In the last lecture, we have seen the Chapman-Kolmogorov theorem actually, but we didn't see the proof of it. We have explained it by using a example, and we have seen that how we can make use of that. We have how we can make use of this theorem to find the probability distribution after some n time steps. Okay, so that's what we have seen in the last lecture. That means we have considered a problem with C3 supermarket A, B and C, and the transition probability matrix, everything was considered, and we have seen what will be the total number of customers after some n time steps. Okay, now we have seen, so this was the theorem basically. So what we are going to see now is the proof of this theorem in a pure mathematical way. Okay, so proof. Okay, proof for Chapman-Kolmogorov theorem. Okay, so that's what proof for Chapman-Kolmogorov theorem. So let us consider three states basically. Let's say we have three states for proving this theorem. We consider first three states I, J and K. Instead of A, B and C, we are considering three states in general, I, J and K. Okay, now we consider two time steps. Okay, two time steps. Okay, that means we are going to see the situation of the system after two time steps. That means the 10th time step n is equal to maximum 2. Okay, and we are also assuming initially the system state, the state was I. That means the system is starting at state I. The system was having state I initially. Okay, that is the meaning. Okay, so the system was having state I. Okay, now it is also having another state J and this is K. So this is the initial state. Anyway, I will represent it by using red color. Okay, so now we are assuming that the system was having initial state I, and we are assuming how it can reach the J, because this is our final state after two time steps. That means that means at n is equal to 2, at the second time step, that means n equal to 2, the state is J. That's what we are going to consider. That means we are assuming that this is our final state at n equal to 2, and this is our initial state at n equal to 0. That is the initial state. Now how we can reach J? Actually, we can reach J in many different ways, right? So we can reach J in many different ways. That is what I am going to explain. We have J as the final states. How we can reach J? Initially, I can start from I. Okay, after that means n equal to 0, and at n equal to 1, okay, I will use the different color. N equal to 0, I was in I, because I am starting from I. This is already, we have already explained this, because we are starting from I. And after that again I move to I at n equal to 1, and at n equal to 2 from I move to j. This is how I can reach j. This is one way for reaching j. Similarly, I started from I. After that, I move to k, and from k I move to j, right? So you can see here, this is the first case I told you, this is the second choice. Okay, so the first choice is nothing but from I again move to I, and after that I move to j. Fine, that's fine. Now another choice, I was in I, after that I move to k, then from k I move to j. Okay, that's how I moved. Okay, I to k and k to j. I use the same color. And next is I was in I. Okay, after that I move to j. That means I was in I. After that I move to j. Then I again stayed there in j. So j to j. So these are all the three possibilities. This is how I can move, right? So I was in I to I, then I move to j. So in the second case, I was in j, then I move to, sorry, I was in I, then I move to k, then to j. So this is, then the third case is I was in I, then I move to j, and then to again to j. I stayed there in j for the time step 2. So these are all the three possibilities. If you closely check this issue, you can see that there are only three possibilities in this problem. Okay, because we are considering actually n is equal to 2, so we have three possibilities here. Now I will rewrite these possibilities again. So j, I need to reach the final state j. How can I reach? I start from n equal to 0, n equal to 1, and n equal to 2. Okay, so I was in I, after that I move to I, then I move to j. I was in I move to k, after that I move to j. Okay, so these are all the final states. So final states, you can see everything is j. Then I was in I, then I moved to j, I stayed there again in j. So these are all my final states. Okay, and these are all my initial states. Okay, in between, you see here, this is in between. Okay, in between. So I want to find the transition probability. So I want to find the probability from I to j with the second time step. You can see here, this is the first n equal to 0, n equal to 1, and n equal to 2. So I want at the second time step n equal to 2. Okay, in general we can say this is this guy, this n is, this is nothing but n equal to 2, right? So we want to find this one. So this we have seen in the last class. By using matrix multiplication we can easily find it, but we are going to prove it. Okay, so with this above notion, I am going to write Pij of the second time step can be written as the probability that, okay, the probability that I was in x0, initially I was in x0, which was I, that means I am talking about this case x0, and I moved to I want the final state x2 as j. Okay, so you can see that this is showing n equal to 2 and this is showing n equal to 0. I was in I and I want to move to j. So this I can do it in three different ways. I told you this is nothing but probability that initially I was in x0, which is I. After that I have got x1, that means the next state, as I, That means I am going to explain this condition, the first condition, this is the second part, and this is the third part. Okay. So you can see here, then I move to I. After that, I move to x2 is equal to j. Okay. That means I have written this one. Okay, the first part. Next, plus or I can have, that means I can say this is the term 1 anyway, the term 1 t1. Okay. Next, I can move in another way also. I was having initial state which is I. After that I move to k, x1 was k. Okay. After that, you see I am talking about this one. Then not this one, okay, sorry, yeah, I am talking about the second case. So x1 is equal to k and x2 is equal to j. Okay. So this I am calling it as term 2 plus, or the third state, actually the probability that I was in, sorry, so this is term 2. Okay. Now the probability that I was in x0 which is equal to I, and x1 I move to j, and x2 again I stayed there in j. That means again I move to j. So these are all, this is the term 3. So you can see here, these are all the 3 conditional distributions, conditional probabilities you can write, and you can reach I in 3 different ways. So the total probability will be sum of all these individual ones. Okay. Now we will take the term 1. Okay, we will take the term 1. So what is the term 1? So the term 1, the t1 I am going to take, it is nothing but the probability that I was in x0 which was I, then I move to x1 which is again I, then I move to x2 which is equal to j. Okay, this is my probability. But I can write this term in a different way, right? So I can write this term in a different way. You can see by using the conditional probability, it is like the conditional probability. So by using the notion of conditional probability, we can use like this. It is nothing but the probability that x2 is equal to j, comma, x1 is equal to I, comma, x0 equal to I, divided by the probability that x0 is equal to I. Okay. This is by using this formula, probability of a comma b is equal to probability of a given b. Sorry, the probability, this is by using this example. Please refer, a given b is nothing but probability of a comma b divided by probability of b. Okay. So by using this conditional, this is the conditional probability. So by using this formula we are writing this. Okay. We have seen this in the first few lectures. Okay. So this is nothing but, again I can split this guy in another way. So I am going to split this again in another way. This is nothing but the probability that x2 is equal to j, given, I am putting here given here now, x1 is equal to I, comma, x0 is equal to I, into the probability of these two. Because if you see this formula, it will be very clear to you if you know this formula. Okay, see, please, this is the reference. So if you see this reference, it is very clear to you. So it is nothing but probability that x1 is equal to I, comma, x0 is equal to again I. Okay, divided by p of x0 is equal to I. So this I can write. So this again I can split it into 2. This is nothing but the probability that x2 is equal to j, okay, given x1 is equal to I. It is because we are talking about the Markov process. Since we are talking about the Markov process, the current state will be depending only on the immediate previous one. That's why x2 is equal to j, then x1 is equal to I, because we are going to omit this guy. We omit because it is a Markov process, that's why. Okay, into the probability that you see here, this part can be again splitted x1 is equal to I given x0 is equal to I into probability that x0 is equal to I by using this reference, okay, that we have already explained. So divided by probability that x0 is equal to I. Now you can see I can remove these two because both are same, okay. So we can rewrite the equation again in another way. So this is nothing but, this is I am just talking about the first term. So this is nothing but the probability that x2 is equal to j, okay, I am talking about this term anyway, okay, x2 is equal to j comma x1 is equal to I given x0 is equal to I. This is equal to the probability that, I will just write this part, okay. Now it is nothing but the probability that x2 is equal to j given x1 is equal to I into the probability that x1 is equal to I given x0 is equal to I, okay. So this is nothing but, in the first, this is nothing but the transition probability. So it is nothing but p from I to j in one time step, because it is having only one time step from 1 to 2. You see here it is from 1 to 2. So one time step, it is a transition probability, it is a transition probability, that's it, okay, multiplied with, this is the initial one, okay. So it is nothing but I to I, okay, it is nothing but pi I, okay, it is from in the first time step. So it was the first time step, that means at n equal to 1 basically. So from 0 to 1, okay. So what is the transition probability? So you see here it is p of x1 is equal to I, x0 is equal to I, means it is the transition probability from I to I during the first time step. So similarly, so you can you have now this term, okay. So this term can be written as the probability that x2 is equal to j comma x1 is equal to I given x0 is equal to I. This is nothing but pij into pi of the first during the first instant, okay. Similarly, you can write in the similar way, you can also write the probability, the second term, I am talking about the second term that we have already considered, okay. This is the term 2 now. So the term 2 we have seen, it is nothing but the probability that x2 is equal to j, x1 is equal to, I am talking about this one, x2 is equal to j, x1 is equal to k, and x0 is equal to I. So similarly I can write like this. So probability that x2 is equal to j, x1 is equal to j given x0 is equal to I. I can write this in like the simplification that we have done for this term. The same way we can write like this. It is nothing but, you see here, this is j, this is I, so I am using ij like this. I will use jj here into pij, okay, of 1, okay. Similarly, this is not for the term 2, I think so. This is for the term 3. Yeah, this is actually, for the term 2 it is j, k and I. You can see here j, k and I, okay, So for the term 2, j, k and I, okay. So for j, k and I, it will be changing, it will be different. So it will be something like this. pkj into pik, okay, in the same way as we have mentioned above. Similarly, for T3, term 3, we will be getting, that means term 3 is, I will rewrite it again, P of x2 is equal to j, x1 is equal to j, given x0 is equal to I, which is equal to pjj into pij of 1. So, our total probability from I to j in the second time step, that is what we have seen in the second time step, pij is nothing but our term 1 plus term 2 plus term 3, that is nothing but pij into p1 pii of 1 plus pkj into pik of 1 plus pjj into pij of 1. Okay, this is what we have seen. Or we can write it as pii of 1 into pij plus pik of 1 into pkj plus pij of 1 into pjj. Okay. So, this can be implemented. This above equation, that means pij of 2, this you see here, this equation can be implemented by using matrix multiplication. Okay. How? Because we have the state transition probability matrix, which is nothing but pii, pij, pik. Okay. Similarly, pji, pjj, pjk. Similarly, pki, pki, pkj and pkk. Okay, that's it. So, if you want to find the second phase, or if you want to find what is the transition, what is the overall response at the second time instant, then you have to just find P2, which is nothing but P into P. If you multiply this P into P, then you will be getting these kind of terms as shown this in the equation. Okay. So, this can be easily multiplied. This can be easily found out by multiplication, matrix multiplication. Similarly, p cube, that means not p cube, actually at the third time instant, that means this is showing the nth time instant, nth transition. Okay, nth transition, the value can be easily found out by p into p square. Okay, this is nothing but p cube. So, if you just simply take the third power of this matrix, you will be getting easily third time instant. That's the beauty of this. So, I want to give you one comment on this. If P is the transition probability matrix of a homogeneous Markov chain, then n step transition probability matrix Pn is equal to the nth power of P, that means nth power of P, P power n. Okay, and this is called the Chapman-Kolmogorov theorem. Okay, so this is the proof of this theorem. Okay, this is the theorem. Okay, so this is how we can find the transition probability matrix at the nth time step. Okay, so we will see some problems for Markov chain. Okay, so the question number 1. the transition probability matrix of a Markov chain xn, which is n is denoting the time step. That means time step can be 1, 2, 3, etc. And it is having only 3 states, 1, 2 and 3. Having only 3 states, 1, 2 and 3 is given by the probability transition matrix, which is 0.1, 0.5, 0.4. Similarly, 0.6, 0.2, 0.2. Okay, 0.3, 0.4, 0.3. So we have already discussed about the transition probability matrix and its meaning. Suppose this is xn minus 1 and this is xn. This is the next state. So the present state can be 1, 2 and 3. Next state can be 1, 2 and 3. This is how we can. So 1 to 1, the transition probability is 0.1, and from moving from 1 to 2 it is 0.5. Okay, and 1 to 3 it is 0.4 and so on. Okay, and the initial distribution is also given, and initial distribution is, that means we have seen one example regarding the supermarket. There we have seen how we can find the initial distribution. So initially the density or the mass function was 0.7 for 1, 0.2 for 2 and 0.1 for 3. Okay, so this is the contribution for 1, this is the contribution for 2, and this is the contribution for the state 3, because we have 3 states. Okay, now the question is, the first part of the question, we will give the question and the answer together. What is the probability that x2 is equal to 3? Okay, I will write the question completely. And second, what is the probability that x3 is equal to 2? That means this is showing actually the nth time instant, n equal to 2, and this is showing basically n equal to 3. Okay, and this is showing the state. The state is 3. Okay, so x2 is equal to 3 and x3 is equal to 2 and x2 is equal to 3, comma x1 is equal to 3 and x0 is equal to 2. That means starting from state 2, it goes through this transition and finally reach the state 2 again in the third time instant, or the third step. Okay, now we have to find okay, that's it. Now we can see it is very easy to find what is x2 is equal to 3. So what is the first part of the problem? It is the probability that x2 is equal to 3. The probability that x2 is equal to 3 means, if you know, you see, you are talking about n equal to 2, so you can find p square and take the initial distribution, which is nothing but this is your p0 bar anyway. So p0 bar, then you will be getting the p0 bar, then you will, it will be usually represented, this is p0, then you will be getting p2. Okay, so it contains 3 probabilities, one here, one here and one here, and you want something which is related to 3, so you take this number, then it will be your probability, it will be your distribution at n equal to 3. So we will find first what is p square. So p square is at the nth time step by using Chapman-Kolmogorov theorem. Okay, CKT I will write by using CKT, we will write like this. So you will get this answer because you can see here p has been given, so you can find p square, so you will be getting this answer 0.43, 0.31, 0.26. okay. Similarly 0.24, 0.42, 0.34, okay, and 0.36, 0.35 and 0.29. okay. This is, now you want to find for x3, so but we will write everything anyway. So p0 was given as initial distribution was given, p0 was given as 0.7, 0.2 and 0.1. okay. So we will find p2 as 0.7, 0.2 and 0.1 multiplied with 0.43, 0.31 and 0.26, 0.24, 0.42, 0.34. So 0.36, 0.35 and 0.29. So this is how we will find. So but we are interested, so this is regarding, I will tell you, this is regarding the state 1, this is regarding the state 2 and this is regarding the state 3, but we need only for the, from the question we need only for state 3. So the probability that x2 takes the value 3 is nothing but, I want only the third state. So what I will do, I will just take the third column and this row and I will multiply together because that will be the third element. So 0.7 multiplied with 0. Okay, I will take like write like this, 0.26 multiplied with 0.7 plus 0.34 multiplied with 0.2 plus 0.29 multiplied with 0.1. okay. So you will be getting the answer as 0.279. So this will be the distribution at n equal to 2 for state 3. okay. So we can also write it in another way, or by using the formula we can write like this. The probability that x2 takes the value 3 can be written as the probability that x2 takes the value 3 given that x0 takes the value I into probability that x0 takes the value I. This kind of method we have already seen, and this I will be any state. I will be from 1 to 3. That means from 1 to 3 it is x0 was, that means I can have I, you see here I can be 1, 2 or 3. That means I start from 1, after that I move to 1, then I move to 2, sorry, then I move to 3, okay, then I move to 3. This is possible. Similarly, I start from 1, okay, then I move to 2, I start from 2, then I move to 2, then I move to 3, okay. I start from 3, then I move to 3, then again stayed there in 3, okay. So that is possible, okay. So these are all the different possibilities anyway, okay. This kind of explanation is not so important for you. Anyway, we can use the matrix theory and solve it, okay. Now we will see the second part of the problem. What is the probability that it has been given like this, x3 is equal to 2, x2 is equal to 3 x1 is equal to 3, x0 is equal to 2. That means it should start from actually 2, then move to 3, then move to again 3, then move to 2. That means it should go through this path only. So how we can solve this? So what I am going to do is that I will take first these two probabilities. After that I will take the whole thing. Okay, that means first 3 probability. After that I move to the whole one. Okay, now we will see what is the probability that x1 is equal to 3 given that x0 is equal to 2. So it is nothing but the probability what is the probability that x0 is equal to 2 and x1 is equal to 3. That means it is nothing but the probability that x1 takes the value 3 given that x0 is equal to 2 into the probability that x0 is equal to 2, right? So from 2 to 3, what is the transition probability that we have seen? Okay, we have already seen from 2 to 3 what is the transition probability. You see this is 2 and this is 3, so 2 to 3 the transition probability is 0.2, you see here. So 2 to 3, okay. So take this value from the so 2 to 3, so it is nothing but 0.2 into what is the probability that x0 is equal to 2. X0 is equal to 2 means the initial distribution. So initial distribution, this is 1, this is for 2 and this is for 3. So for 2 the initial distribution is 0.2 from this. So into 0.2, that is 0.04. Okay. Now we will consider these 3. That means the probability that x2 is equal to 3, x1 is equal to 3 and x0 is equal to 2, right? So this I can write as the probability that x2 is equal to 3 given that x1 is equal to 3, comma x0 is equal to 2 into the probability that x1 is equal to 3, comma x0 is equal to 2. But you know that this is a Markov process, so I can omit this part because it is a Markov process. Omit, this part can be omitted. It is because Markov process at time step 2 will depend only on the time step 1. Okay. So this is nothing but the probability that x2 is equal to 3 given x1 is equal to 3 multiplied with, I am going to split this guy again. This is nothing but the probability that x1 is equal to 3 given x0 is equal to 2 multiplied with probability that x0 is equal to 2. So this I can write as x1 is equal to 3 and x2 is equal to 3. That means 3 comma 3. So you see here this is 3 and this is 3. So it is nothing but the probability is 0.3. Okay. So 3 3. We will take that position. That means we will take the value from that position 3 3. Okay. 0.3 multiplied with, we have already seen this guy. Okay. We have already seen that x1 is equal to 3 and x0 is equal to 2 means we have already seen the value was 0.04 multiplied with x0 is equal to 2. Probability that x0 is equal to 2 is nothing but, sorry, not this one, this is the x0. So probability x0 is equal to 2 is 0.2, right? Am I correct? I hope so. Okay, it is 0.2, right? 0.2. So we will be getting x2 to x3, what is the value? Okay. Okay, so into probability of let me check. Okay, this is not required anyway because we have already find it, sorry. So into this I can write it directly into probability of x1 is equal to 3 and x0 is equal to 2, and we have already found out this, so we don't need to calculate again. So it is nothing but 0.04. We have already got the answer. So this is nothing but 0.012. Okay, I hope this is clear to you. Now we will take the whole thing. That means I told you we will take the whole thing. That means from the first to last. So the probability that x3 takes the value 2, x2 takes the value 3, x1 takes the value 3, and x0 takes the value 2 is nothing but the probability that x3 is equal to 2 given that x2 is equal to 3, x1 is equal to 3, x0 is equal to 2 multiplied with the probability that x2 is equal to 3, comma x1 is equal to 3, x0 is equal to 2. So this I can write, this part I can write as probability that x3 is equal to 2, x2 is equal to 3 by definition of Markov property or Markov random process. We can write like this, multiplied with probability that x2 is equal to 3, x1 is equal to 3, and x0 is equal to 2. But we have already seen what is the answer for this. It was 0.012 multiplied with, and this is the transition probability. So if you see the transition matrix, you can easily write it. It is from 2 to 3. So this is 2 and this is 3. So 2 to 3 it was 0. It is 0. Let me check. 2 to 3. Okay, 2 to 3 is 0.2, I think so. Okay, not 2 to 3. Okay, sorry, it is not from 2 to 3, it is from 3 to 2. What I have written, yeah, it is from 3 to 2. Okay, if you see the table 3 to 2, so this is 3, sorry, this is 3, this is 3, and this is 2. So you will get at 0.4. Okay, so 0.4 multiplied with 0.12, that means it is nothing but 0.0048. This is the probability, okay, for this one. I hope this problem is clear to you. Now we will see another problem. Question number 2. A fair die is tossed repeatedly if x of n denotes the maximum of numbers, occurring in the first n tosses. Find the transition probability matrix P of the Markov chain. Then find also P square and the probability that x2 is having a value 6. Okay, So this is the problem. That means there is a dice which has been tossed repeatedly, and xn denotes the maximum number of numbers occurring in the first n tosses. Suppose if you are tossing a dice for the first time, you may get for n equal to 1, you may get the outcome 1, 2, 3, 4, 5 or 6, okay, anything, 1 or 2 or 3, okay, everywhere there is some or anyway, don't worry. So 1 or 2 or 3 or 4 or 5 or 6, you can get any of these outcomes, and you will be taking the maximum of it, okay. Suppose you are getting 1 for the first trial, then for the second trial actually this 1 will be excluded, okay. So like that. So the second trial actually it will be considering it will not contain actually this 1 if you are getting 1. If you are getting 3, the second trial will be containing from 4, 5 or 6, okay. It is because you are taking only the maximum of the numbers occurring in the first n tosses. So we can write the transition probability the matrix. Suppose we have, for example, if nth toss was 3, having an outcome 3, then xn plus 1 maybe, you see here you will not be taking into account this 1 or 2 or 3. So whatever you are getting, okay, in the nth outcome, if you toss the coin you may get 1, 2, 3, 4, 5 or 6, okay, anything. But whatever you are getting in the n plus 1th, if you are getting n plus 1th, if you are tossing for the next time, you may get all this with equal probabilities, okay. Actually it is having equal probability, everything is having equal probability, but the problem is you will be taking the maximum, you will be taking only the maximum, and also you will be taking the maximum of the numbers occurring in the first n tosses, okay. So if you are getting 1, you may directly take it or not. No, suppose in the nth toss you have got already 3, that means that if you are getting 1, if you get 1 or 2 or 3, you may take 3, because in n plus 1th toss, because in the nth toss you got already 3. So the probability that you choose the value 3, in the n plus 1th time instant, given that in the nth time step it was 3, is nothing but, that means the probability that in the n plus 1 time instant you may get the value 3, given that in the nth time instant it was already 3, is nothing but, even though if you are getting 1 or 2 or 3, you may choose 3. That means it includes the probabilities of 1, and it includes the probability of 2, and it also includes the probability of 3. That means 3 by 6. So this is how the transition is calculated, okay. Now we will see how we can write the transition probability matrix. So in the nth step, you can take, this is the nth step and this is the n plus 1 step. That means you 1, 2, 3, 4, 5 and 6. Here also 1, 2, 3, 4, 5 and 6. Suppose in the first, that means in the nth trial, suppose in the nth time step you got 1, that means in the next time step also you may choose 1 or 2 or 3 with equal probabilities. because there is no number which is less than 1. Now suppose in the nth time instant, suppose you got 2, then in the n plus 1th time instant you may not choose 1, because you have already got 1 in the previous trial. So the probability of choosing 2 is more here, because 2 may come from, even though if you are getting 1 you may choose 2, because you have already got 1 in the previous trial. Okay, so even though if you are getting 1 in the current trial, because you have already got 1 in the previous trial, so in the next trial, suppose if you are getting 1, you may not choose that 1, because you have already chosen 1 in the previous trial, from the previous trial. So in the next trial, if you are getting 2, that 2 will be having more probability. It is because it is having a probability from 1 and it is having the probability from 2. Okay, so you are choosing only the maximum number, so this will be 0. That's what we have explained here. Okay, that's what we have already explained here, because you will be choosing only the maximum number. Similarly for 3 there is no issue, 1 by 6, 1 by 6, 1 by 6, 1 by 6. Now in the nth trial, suppose you got already, suppose in the nth trial you have already 3, so in the next trial if you are getting 1 you may not be choosing it, so the probability of 1 will be equal to 0. In the next trial if you are getting 2, then also you will not be choosing it, because the probability of 2, that is why it is equal to the probability of 2 equal to 0. Suppose in the nth trial you have already 3, then in the n plus 1th trial also you may choose 3, is 3 by 6. How it is coming? It is because if you are getting 1, then also you will be choosing 3. Even though if you are getting 2, then also you will be choosing 3. Okay, so if you are getting 1 in the next trial, then also you will be choosing 3, because you have already 3 from the previous trial. Similarly, if you are getting 2, then also you will be choosing 3, because you have already 3 from the previous trial. If you are getting 3, then also you will be choosing 3. You have already 3 from the previous trial. So the probability of getting 1 is actually 1 by 6, 2 is actually 1 by 6, then 3 is also actually 1 by 6. So the probability of choosing 3 is 1 by 6 plus 1 by 6 plus 1 by 6, it is 3 by 6, and the remaining will be saying 1 by 6, 1 by 6. If you are having 4 in the previous trial, then in the next trial if you are getting 1, you will be choosing again 4. So you will not be choosing 1. So the probability of 1 is 0. 2 is also 0. 3 is also 0. If you are getting 4, then it is nothing but 4 by 6, as explained before. Okay. Similarly 5 you will see like this, 5 by 6, 1 by 6, 0, 0, 0, 0, 0, 6 by 6. Okay. 6 by 6 means 1. Okay. So what is the meaning of this? In the nth trial you have already 6, then if you are getting 1 you will not be choosing it. If you are getting 2, then also you will be choosing 6. If you are having 3, then you will not be selecting 3. Okay, you will be selecting only 6. So everything is moving towards 6 now. That means the probability of 6 will be 1 by 6 plus 1 by 6 plus 1 by 6 plus 6 times. That means 6 by 6. Okay, this is the transition probability matrix. So the second part of the question, find also p square. Okay, what is p square? So we can find the p square is nothing but p into p. So you will be getting it as 1 by 36, because everything, all terms contain 1 by 6. 1 by 6 into 1 by 6 is 1 by 36. So it become 1, 3, 5, 7, 9, 11. Then 0, 4, 5, 7, 9 11, then 0 0 9 7 9 11, 0 0 0 16 9 11, okay, then 0 0 0 0 4 zeros 25 11, then 0 0 0 0 0 36, okay. This is the p square, okay. Next part of the question, let me check what is the next part of the question. What is the probability that x2 is equal to 6? x2 is equal to 6, that means you want to find the probability that what is the probability that x2 takes the value 6. That means the time step is n equal to 2, okay. So what is the initial probability? P0, initially you can get any value. That means if you are tossing a dice, you may get 1 by 6, 1 by 6 and so on. This is your initial probability, okay. So at time step 2, you can find the probability as initial probability is P0, then you have to multiply with p square, okay. This is the time step 2. After that you have to take, so this is, you will be getting it as 1 by 6, 1 by 6, 1 by 6, 1 by 6, 1 by 6 and 1 by 6, okay, 6 values multiplied with the p square, okay. So you will be getting p2, okay. This is, now you will be considering only the last value, okay, or you can represent like this. It is nothing but 1 by 6 multiplied with pi 6 in the transition probability matrix, okay. pi 6 in the second pi 6 means it is the sixth column, that means pi 6 of this matrix, okay, this matrix, and I varies from 1 to 6. This is nothing but the probability that x2 is equal to 6. So you can do it in two different ways, okay. So you can multiply by using this matrix multiplication and take the sixth element from this product, okay. Then you can check it, you will get this answer anyway as 91 by 216. This is the answer, okay. I hope this part is clear to you. Next we have one more problem. So you see here the question is, a man either drives a car or catches a train to go to office. So a man, this is a man and this is his office, okay, and he may go by car, this is his car, or sometimes he may go by his train, so this is the train, okay. So he may go by train, so he has two choice, one by car and one by train, okay, to go to the office, okay. He never goes 2 days in a row by train. That means suppose on day 1, he goes by train, then day 2 that means he never goes 2 days in a row by train. In the day 2 he will not go by train, he will use his car, okay. Now then if now the next part, then the next day, that means okay, 2 days in a row by train, but if he drives one day, suppose on day n, this is day n and day n plus 1, you can say. On day n, suppose if he drives, that means he drives, he uses his car, then the next day he is just as likely to drive again as he is to travel by train. That means in the next day he may use the car. In the day n plus 1, he may use the car or train with equal probability. That means he is just as likely to drive again as he is to travel by train. That means these probabilities are equal. That's it, equal. Okay. So in day n, if he use the car, in the next day also he may use the car or train with equal probabilities. Okay, that's it. Now suppose that on the first day, of week, how he is taking his decision? Okay, he will toss a die. And if the outcome is 6, then only he will use his car. Okay, that means he will drive to the work. That means he will use his car. That means if so, on the first day of the week, on the day 1, you can say he will toss a die, and if the outcome is 6, then he will take a decision that okay, today I will go by car. Okay. Now if he is using this strategy, find the probability that he takes the train on the third day, and also you have to find the probability that he drives to the work in the long run. So first of all, for this kind of problem, what is the initial probability? First of all, I want to tell on day 1. So regarding day 1, okay, on day 1, how he is taking the decision? He toss a dice, and if the outcome is 6, he takes the car. Okay, so I will use the notation this T for train and C for car anyway. Okay, so what is the probability that he choose the car? If the outcome is 6, then he will be choosing the car. So what is the probability to get this outcome? It is 1 by 6. So what is the probability that he choose the train? It is it is 5 by 6, because if he don't choose the car, automatically the probability of train will be 5 by 6. 1 minus 1 by 6 will be 5 by 6. So the initial probabilities on the day 1, I will say on the day 1, for the train, this is the probability of train and this is the probability of car. What is the probability of train? It is 5 by 6, and probability of car is 1 by 6. This is the initial distribution. Okay, how it is distributed initially. Now the transition probability matrix, that's what I am going to define now. The transition probability matrix P, that means this is the nth day and this is the n plus 1th day. Okay, in the nth day he may choose the train or car. In the n plus 1th day also he may use the train or the car. So I can write like this. Now I have already told you that suppose he goes by the train on the nth day, in the n plus 1th day he will never use the train, he will use the car. Okay, that means if he choose on the nth day train, then on the n plus 1th day he will never choose the train, so that the probability will be equal to 0. So the next day actually he will be using the car, the probability will be 1. Now, the second part actually from the question we have seen, suppose on the nth day he used the car, then on the n plus 1th day also he will use the car or train. Suppose he used the car, then the probability that he may choose the train is 1 by 2. He may use the car is also 1 by 2. So, this is how, that's it. So, this is the probability transition matrix. So, this is very simple problem. So, the only thing is that you should know how to formulate this transition probability matrix. This is transition probability matrix, TPM. Okay. So, we got the initial distribution, that means P of 1 is 5 by 6 and 1 by 6, because this is for the train and this is for the car. Okay. And the probability transition matrix for train, car, this is train and car, it is 0, 1, 1 by 2 and 1 by 2. Now, we will see how to solve this. Okay. What is the first part of the question? The first part of the question, the probability that he takes the train on the 3rd day. Okay. The probability that he takes the train on the 3rd day. So, how we can find the first day information we have? This is for the first day. Okay. For the first day he may take the train is 5 by 6. It is already there. So, P on the 3rd day means P of 3. It is nothing but P of 1. If you know P of 1, you have to multiply with the P square. That means if you multiply with P square, or we can write it in. So, we want to find P of 3. This is the question. So, what is P of 2 on the 2nd day is nothing but P of 1 into P, and P of 2, sorry, P of 3 3rd day means P of 2 into P, which is nothing but P of 1 into P multiplied with P. That means P of 1 into P square. Okay. If you do this calculation, I am not going to solve this completely. You know what is P and what is P of 1. That means P of 1 is 5 by 6 and 1 by 6 into P square. P square you can find it. Okay. So, you will be getting it as P of 3, you will be getting it as 11 by 24 and 13 by 24. So, the first value actually stands for the train and the second value stands for the car. The question is that we want to find on the 3rd day what is the probability that he takes the train. So, for the train, the probability that the man travels by train on 3rd day is 11 by 24. That's it. Okay. Now, on a long run, that is the question. That is a very beautiful question. That's what I want to spend some time. Now, what is the probability that he drives to the work in a long run? You see the term long run. Long run means as time tends to infinity. Okay. So, as time tends to infinity, that means on a long run, what is the probability that he drives? That means he uses car. Okay, he drives to work. That is the question. You see here that I told you that if you know P1 or P0, you can find P2 as P1 into P. You can find P3 as P2 into P, which is nothing but P1 into P square. Similarly, you can see suppose P8 as P on the 8th, there is no 8th day anyway. 8th day means the first day of the next week. Okay, not the first day of the next week. Suppose if you are, okay, sorry, that's not relevant here anyway. Now, P6 you can say it is nothing but P5 into P square, and P7 on the 7th day means P6, sorry, not P, P5 into P, okay. So P6 into P, which is nothing but P1 into P6, P power 6. So this is how. So if you calculate like this, you can find that as the days approaches, or if he is using this strategy for a long run, that means for 1 year if he is using this strategy, then we can see that this guy may be what will be the final distribution of this Markov chain, okay, the stationary state distribution. So how to find this? So we will choose, if we proceed like this, this is pi will be, I told you that the Markov chain will be converging to a particular value as time times, this is equal to some pi into P is equal to pi. That means this is nothing but this initial distribution of pi 1, this is pi 2. That means this is for first one is for the train, this is for the train, and this is for the car, right? This is equal to some pi 1 into pi 2 into P, okay. So I am going to write the steps: pi 1, pi 2 into 0, 1, 1 by 2, 1 by 2. With this will be same as pi 1, pi 2, pi 1 and pi 2. Why it is so? On a long run, we can see that this Markov chain is converging to a particular value. So if you are getting P6, you will be getting it as same as P7, for example. This is an example. Similarly, you can see that it is same as P8, that means the 8th day is not there anyway in this problem. But in general, we can say that as the time progresses, as time goes to infinity, Pn plus 1 will be equal to Pn. So in general, I can give it as pi. But how to find Pn plus 1? Pn plus 1 can be found out by Pn into P. But this is equal to some pi, this is also is equal to pi. So pi is equal to pi into P. So what is this pi? That is the final distribution after a long run, and that can be found out by solving this equation. So solve this equation and find pi, okay. What is this final distribution? So from this equation, I can say here pi 1 into 0 plus pi 2 into 1 by 2 is equal to pi 1. That means pi 2 into 1 by 2 is equal to pi 1. So this is one equation. Similarly, I can write another equation: pi 1 plus pi 2 into 1 by 2 is equal to pi 2. So this is another equation, okay. Now I can solve these two equations. So instead of pi 1, I can substitute pi 2 into 1 by 2 and solve this equation. So solving this equation, I will get pi 1 is equal to 1 by 3 and pi 2 is equal to 2 by 3. So pi 1 stands for the train and this for the car, pi 2 for the car. So what is the conclusion? That means therefore the probability that the man travels by car in the long run is nothing but, you see here this number, this stands for car and another one for train, that is 2 by 3. That means 66% of the time, as in a long run, suppose if you are observing this phenomenon for a year, you can see that this person is traveling most of the time, that means 66.6% of the time, that means 2 by 3 means 66.6%. Okay, this is 66.6%, and this is 33.3%. so most of the time this guy is traveling by car. Okay, that is the final observation. Okay, if this is repeated for a long run. Okay, I hope this is clear to you. Thank you.